class, we talked about Euclidean metric and taxicab metric. And do you see any problem with the formula?
Should the absolute value be squared?
No.
Okay.
No, that's the point of taxicab matrix, that we don't need we don't do that.
I just wondered. I didn't really know about that until you mentioned it yesterday. So that was
right. So this is it. So each term here is this, and then for each dimension you have, if in 2 dimensions you have only 2 streets, and if you have 3, go left, right, up, or forward and up. That's going to be 3. So no, there's another problem with it.
Should there be an n above your?
That is certainly is on the other side, but it's not, strictly speaking, a mistake. Not a big one. What's the big one?
Should it not have the radical?
It should not have the radical. So that certainly is a mistake. Okay, so so you don't see it in class. Well, if you see it in class, you say it in class. If you don't see it in class, we can review the video, and then you just put it in comments. Minute 3 of the class. This is the error. You know. You can put it in the form of a question if you prefer, but it is actually more impressive if you put it in an affirmative statement. So that shows confidence. So don't just say isn't that should be, as it was just shouldn't be, should it have the square root? That's fine, but you can say no, that's wrong. You're wrong. Change that. So that shows confidence. So in your knowledge. Okay, so. So this is certainly it's a fun topic, but it actually is not gonna. I don't believe it's gonna reappear in this class. Certainly fun to know, but we're not gonna deal with that. Okay. So any other questions? If you don't do YouTube, I don't know, maybe Facebook or something else. Anyway, so just find a way to show your participation. Okay, so let's review. So we are done with the metric, and we started the vectors, topic of vectors. The idea is to begin with, if you want to connect to what we have been talking about, it is the displacement from one location to the next. We're talking about points in those spaces. And if you combine them together in order, point P and Q, then you can say that from P to Q, that's displacement. We can think of it as a vector, and secondly, we can think of it as a subtraction of those points. So if you really want to think algebraically. Okay, so it is helpful why P minus Q is a good idea, because then P minus Q is equal to negative Q minus P. Okay, so moving from P to Q is the opposite vector of displacement as moving from Q to P. Okay, so that's algebra is very convenient. Okay, so but that is really the abstract setting of those Cartesian spaces of any dimensions. But really the vectors come from the physical space, and that's strictly speaking from physics. Okay, so in other words, we would be talking about what forces and velocities. Okay, so let me go over those things. So you can think of it as motivation or starting point or interpretation or metaphor of vectors. So if it is R1, R2, R3, so it's a physical space, then we are talking about velocities, say forces, or accelerations, and velocities. Okay, so these are vectors. Okay, and that is why in this setting, the R1, R2, R3, really the Cartesian coordinate system is not necessary for this to make sense. In fact, there are no Cartesian system in these spaces. So that's why that's why I started doing things without Cartesian system, but rather just a geometric analysis of those vectors, how we do algebraic operations with them. Okay, so here's you can interpret the you can interpret Forces and velocities, certainly not the same thing, but it is worthwhile to look at both to realize how they interact with each other. So an object with forces applied to it, usually you can visualize forces by, say, pick a specific one, say a spring is attached to an object. Okay, so or more than one. So one spring like this, and the other one like that. Okay, so then you do know that, and the question then becomes which way it's going to go, which way the resulting force will be pointing, and we know roughly that it will be roughly in the diagonal direction. If the two springs are identical, then it will be definitely halfway between them, but the magnitude will depend on that angle, and we already know how to work that out. We end up with a parallelogram. Okay, so the resulting force going this way. Result. So say this is A and this is B. Result is A plus B. Okay, so that's how we add. This is how we add forces. Okay, and then to begin with, and then so that's just two-dimensional. Well, the whole thing actually, let me make it clear. So the algebra is low-dimensional. I mentioned that last time. So adding vectors will remain within the plane of those two vectors, those two lines. And the scalar multiplication is a little less than that. It is a one-dimensional. So one thing to mention here is, what if you can have a spring attached, say A, or you can attach a spring that is longer or shorter. Okay, so once again you might be interested in, say, 1.58. Okay, so it's attached in the same direction and made of the same material, but it is longer, and longer presumably is a stronger pull provided by that spring, and then you want to compare them, and that would be scalar multiplication. So scalar multiplication. While this is a vector addition. So that is these are the ideas of physics that are brought into mathematics, and then spread out as we will into the rest of the those spaces, okay, including abstract spaces. Okay, so that is the forces. Forces are understood here, how they interact through springs, visualized with springs. Once again, longer spring is a stronger pull, and then they may have different directions, and they can be edited, and we have these two algebraic operations. Okay. In the meantime, you can have the same with velocities. So how do we interpret velocities? Say you are maybe maybe you're on a train. And train is running with speed v, and then velocity v, a in some direction, and then you're going like this. Also within the train, you are walking forward, for example, or backwards. Then together, your actual motion, you will be moving with the velocity. The resulting velocity is a plus b. Okay, so that's roughly how you can also interpret easily the vector addition for velocities. So mathematically speaking, these are vectors. These are vectors. Those are vectors. That doesn't make any difference. The operations are the same in nature, but it's nice to have interpretation, because every time we'll be going back to physics just to visualize things. So either forces or velocities. This is one-dimensional. You certainly can think of velocities one-dimensional. Say maybe if this is the train moving forward, and then you're walking this way, so the whole thing becomes two-dimensional. Or you are going to the second floor of that cart or something like this. Maybe you're going like this. So then once again, it's two-dimensional. So if you're walking up. Okay. So that's all here. The scale multiplication is slightly harder, but you can certainly think of, say, 1.5a. What does it mean? It means your train, go faster by this proportion. Okay, so so back to my picture here. Once we set aside the physics and we look at purely at mathematics, we do addition of vectors head to toe, ignoring all the issue for the time being of the coordinates in coordinate system, and then we have these two operations: scalar multiplication and addition of vectors. So it is not, however, the end of the story, because we have to develop algebra. Let's a little bit beyond this. The algebra is now properties, is what I'm talking about, of algebraic operations, of vectors. Because once we start writing algebraic operations, at the very least, we have to make sure that everything works out the way it works out with numbers. And after all, these vector operations, n equal to 1, this is the algebra of numbers. Okay, so once again, if n is equal to 1, our space becomes straight line, but so every number is a real number, but we could multiply real numbers, we can add real numbers. So the new operation, we're using the same language, addition and multiplication, and now does it match our understanding of these operations as we know, as they apply to numbers. And that requires us to look at at how they interact with each other. But first of all, within each of the operations, we have to see that everything works out. For example, there's a bunch of properties, so I would probably easily miss a couple. But let's say, so we start with scalar multiplication. We'll say A, B, B is equal to A, B, B. Okay? So in other words, you stretch the vector by factor of b, and then you stretch it by a vector of a. It is equivalent to stretching by the vector a by the factor a times b. Okay. So as you get, these are two different things, and for numbers we certainly know this is true, but these are two very different things on the face of it, because in the parentheses here we start with v, then we multiply by b, which is a new vector. And then we multiply by a in order to create yet another vector. So, and then it turns out that there's a shortcut that you can just take those two factors, multiply, and then you have the vector. So it seems kind of trivial, because there's considering how we actually geometrically build scalar multiplication, is a purely stretch. Okay. Another one, how about this? A plus b. V is equal to a v plus bv. That one actually has, well, all of them have names, so I don't want to bother you with names, but this one is, maybe you might tell me what the name of this property is? It is the distributive property, except now we're going to have more than one. Because, well, yeah, as you'll see. So this is, right, so this is a combination of, on one hand, on the left, we have, this is operation on numbers. The a and b are numbers, so we just added them together just like we always have. So there's nothing new here, so that's very old. Over here, this is scalar multiplication. And then we have scalar multiplication here and there. And then lastly is this. This is vector addition. There is no vector addition on the left. Okay, so that's the distributive property. This is that is actually called associative property. But this you can recognize how we distributed v over addition a plus b. So that works out too. You could illustrate why this is the case. Let me try to make that illustration clear. So if I have my vector v, okay, and then I stretch, so v, and then I stretch it by factor of a, say a, b, and then I have my say BV. Okay, so then the idea is that the whole thing is one-dimensional anyway. So we sort of factor out. If you read it from right to left, it's not distribution, the opposite of distribution, which is factoring. So if you read it from right to left, we're factoring V out of this. So okay, so as you can see now, if I take these and I take my AB and add over here BV, I get head to tail, right? So then you can see the length of this is A plus B. Okay, so which means that the whole vector here is indeed A plus B. Okay, so it's think about as if it's V is simply our axis, and in that direction we have stretching it not consecutively as in property 1, but we add them together. Okay, so these are two properties, and then well, the one thing is probably a good idea to remember, which is I mentioned before. It is the interaction between the scalar multiplication and addition is simply x plus x is equal to 2x. Okay, so once again, we define two new operations, and they meet together in this very simple equation. Scalar multiplication on the right, vector addition on the left. It is the same thing. But the property number 2 is just more general. So this one, well, here's another one. So that's distributive property number 1. There, what's the other distributive property number? Distributive property number 2 is, instead of looking at addition of numbers, we would be looking at addition of vectors. So can you suggest what it should look like? So another distributive property. We have two additions now, see? That's the trouble. We're adding numbers, we're also adding vectors. It's not exactly the same thing.
So, given a scalar, say A,
Yeah.
two vectors V and W.
Okay.
A
V,
times,
what? V and then,
W, or V or U maybe?
no, what?
Oh, I'm sorry. So A times the quantity V plus U is equal to
Yeah.
ABV.
What's A? Okay, so as you can see, this looks very similar to the last one, but it is absolutely different because addition of numbers is replaced with addition of vectors. Over here on left, that's addition of numbers, that's addition of vectors. And as you can see, the number 2 property is way simpler because everything stays within one vector, and so it's just a matter of stretching. But this one is actual addition is carried out. So let me then it's worth illustrating for say A equal to 2. Well, if A is equal to 2, you certainly can see what's happening. It's a 2u plus v, and it is equal to u plus 2v. Okay, so let's try to visualize that. So if I have v here and I have u there, okay, so let me look at the right-hand side first. So I'll take the sum. Okay, let's make the sum. U and v, I take the sum like this. So like this. Okay, so this one is u plus v. As you can see, I've been using capitals for the vectors in lowercase for scalars. It just gives you a clue what's going on, even though in the context usually you just either say or you actually point out that this is scalar, a number, and these are vectors. So usually it is spoken out, and therefore there is no ambiguity. Yet still, a notation it helps a lot to understand what's going on. In the book, sometimes they use notations such as for vectors they use boldface. So like this would be even not capital, but like like this. Okay, that is hard to do with a pen, so I'm using capitals. Okay, so that is the left-hand side. Left-hand side, well, actually, make it clear. So u v is given, okay, and then I have computed the left-hand side of our equation. It is u plus, sorry, no, not just yet. Now I multiply by 8, which is 2. I don't think it's going to fit. Select. Yeah, this is also not perfect software. It just, well, I want to select to move it a little bit, and then I don't see, I don't think there is anything on the surface. Maybe edit, still not. Okay, here it is. This is how you do it. Okay, here it is. And I think I can just move it. Okay, so I can continue with my construction. So to finish the left-hand side, I want to now, I take this one and multiply by 2, right? So 2u plus v is what we have on the left-hand side. So I multiply by 2, and this is it. No, that's not good. Okay, so that's also u plus v, capital, and then the whole thing is 2u plus v. Okay, so that's the end, 2u plus v. So that's the left-hand side. Now take the right-hand side. Okay, so what do? We multiply two vectors, each of them by 2 first, and then add. Okay, so I multiply this by 2. So this is also v, and the end result is that's, I can get a good job here with the addition. Okay, now let me finish the right-hand side, and then everything will fall into place. Okay, so this is v. The end result is 2v, right? Then I do the same with u. This is u. So u is repeated twice, and the end result is 2v, 2u. Okay? And then I'm supposed to add them. Be careful here. Okay, so now I'm trying to add them like this. Okay. Okay. So I'm adding. So this is there's a vector at the end with the same initial point. Naturally, they all are. And this is 2u plus 2v. Okay. In the meantime, the green one is this. Improve this. The picture is actually quite simple, and probably next time I'll just do it with Excel. Okay. Let me have some more here. So we have 4 parallelograms. Yeah, I promise I'll do it better with this. So these are supposed to be 4 parallelograms, and they create and they cut one big parallelogram cut into 4 parallelograms. Okay, you see? So 4 parallelograms. Understand what parallel? Okay, that's better. Okay, so the side of each of the bottom parallelogram and the bottom edge and the top edge is 2v. Okay, and the left and right sides of the parallelogram are 2u. Okay, so this is once again this is u and this is u2, just shifted, and this one is v and this is v. Okay, so either we add these two together first, getting a green vector and then multiply it and do it one more time twice, or we do it stretching first vertically, first u and then first v, then u, and then adding them together. The results are supposed to be the same. It does seem to be the same. Okay, so I'll do what I started doing last time, and that is the Excel simulation. So all I have to do is just to do this with more than just multiply them by constant. But this is addition of vectors illustrated in several ways. So it is head to toe on the right, and not head to toe, head to tail, but at the same time we see a parallelogram right here. So all I have just to do is to repeat this 4 times, and that gives me the the distributive property. Okay, so what's at the top is to be discussed, and that is the actual coordinate representation of vectors. So I am trying to avoid it for as long as possible. So because we are invoking pretty much the physics of our three-dimensional space, and things such as velocities and forces. Okay, so these are the 3 properties there. They're more and more. Say number 4 is A plus B is equal to B plus A. The commutative property. Another associative property, A plus B is equal plus C is equal to A plus B plus C. Well, the first one is certainly easy. The number 4 is easy to visualize because there is nothing to visualize. It's just the whole construction of how we build that parallelogram. It does not depend which one you start with A or B. The result is the same. The second one, however, it is different. The number 5 property, it is another associative property. It is also can be illustrated algebraically, geometrically with a similar picture. So let me do that. So number 5, again, A plus B. Let me start with A plus B plus C is the same as so we added A plus B first, then we added C, or we add B plus C first, and then we add A. Okay? The result should be the same. Think about this, by the way, this idea does not really apply to, I don't think it applies to, well, actually it applies to forces, I suppose. So suppose you have 3 forces acting. It doesn't matter which way you're going to add them up together. First, the order doesn't matter, either first 2 and then the third, or vice versa. The order produces the same result. But another way to think about is displacement. So I move from A to B first, and then to C. Or that works actually. Okay, so we'll let me start with A, B, B and C. Okay, let me try doing this separation. So okay, so A plus B first, and once again head to tail, like this. And then this is A plus B. And then I do head to tail it again with C, which is almost horizontal like this. So this is C, and then this is my A plus B plus C. Okay, so that is my left-hand side. This one. Okay, and now I'm doing the right-hand side, but instead of I'm doing B plus C first. Okay, so let me do that. So I have my B, and then I head to tail. I do C, like this. The result is B plus C, and then I add A, like this. Well, it's plausible, even though it's not probably perfectly drawn, but this is A plus B plus C. Same starting point. Okay, so that is associativity of addition. Associativity of addition of vectors, not associativity of numbers. And as you can see, it is plausible. It is pretty much the same quadrilateral. Probably could put these together in order for this to be visible. Well, I mean, you can imagine that these two, if you A plus B plus C added together, then you'll see that they are just I don't think I can right now have a way to visualize it easier, so just by the next time I'll do a little Excel demonstration to see this, in addition to what I already have promised. Associative, distributive, commutative, 5 properties. There are some more. There are special vectors and special numbers. The special number is, of course, 0. So that is why we have another property. It's not really a property, but A, 0 times A is equal to 0. So as notice how differently I'm writing things. So this is a number, and these are 2 vectors. Okay, so let's say property number 6, the 0 vector. The 0 vector, which reflects either no forces involved whatsoever, or there is no, the body is at rest, so there is no velocity, and so the algebra is if you multiply your vector, whatever it is, by 0, the number, then you end up with a 0 vector, and I'm trying to put it, capitalize it. So that's on the right is actually capital O to stand for the 0 vector. You know, sometimes you just say 0 using the usual 0. Not sometimes, but actually most of the time you just simply use the same number 0 for both numbers and the 0 vector. Okay, so and then you can guess what else. 0 plus A is equal to A. There are just so many properties that it's hard to imagine. The thing is that if not, you can write any kind of expression with vectors and numbers, as long as it makes sense, you can transform it in a manner that is familiar. So any skills that you have learned from algebra of numbers is applicable as long as the expression itself makes sense. So you don't try to divide 2 vectors. It does not make sense to begin with, or multiply 2 vectors. So as long as whatever you write makes sense on its surface, you can simplify or manipulate it in the same manner as numbers. Okay, so now coordinates. So coordinate representation, coordinates and vectors. I'm jumping right away from dimension 3 to higher dimensions. So R3 and up to R3, we're still referring to the physical space and some metaphors for the vectors such as velocities and forces. But then we'll once move on to R4 and higher, Rn. What are vectors? Vectors are remember what as we introduced them. Vectors are pairs of locations. So PQ is a vector, is sometimes, I'm not going to do that, but sometimes you may have seen this, right? So an arrow putting on top of it, it is redundant. As long as they preserve the order, I know that PQ is not the same as QP. Okay, so as long as we know that there is no danger of any confusion. So I'll stick with just P and Q. So 2 locations, P and Q are locations in Rn. And if I either subtract them or just align them, put them in a pair, ordered pair, then this is PQ. That's the whole idea of vectors. Then for the time being, it is until we get to calculus, again back to calculus, we are not going to worry about, we don't want to be concerned or worried about vectors being that you are able or unable to add. So we assume for the time being that all vectors that we are studying start at at the origin. Remember, we can add two vectors as long as they have the same starting point, and that point could be any point. So, but it is the, I'm starting vectors at 0, or I'm starting vectors at some point P elsewhere. The properties are exactly the same, so we don't have to worry about it. But otherwise, let me make this comment first. So that's the definition. The components of vector OP, O stands for the origin. Components are the coordinates of P. That's the definition. It makes perfect sense. So we're looking, the origin is where it's supposed to be at 0, right here, and then what we're looking at is the endpoint of our vector. This is my vector OP, and where is that vector? What determines the vector? It determines by the endpoint, because once again the tail, the initial point, is fixed for the time being. So all we have to do is to look at the coordinates of the endpoint. Okay. Well, specifically like this. Say my vector is this. So this is P, and it has coordinates 1, 2. Okay, then on the other hand, OP, this is the notation. 1, 2. We put it in triangular brackets. Alternative notation is this. It is put in a column. We'll see in the future why this is a better way to better notation. Unfortunately, it is so vertical that it takes so much room that a lot of the time we prefer stretch it horizontally. Okay, so once again, depending on the dimension, you have if dimension is n, you have n coordinates of every point, and now every vector has n components. The word is slightly different, easy to confuse, not a big deal. Just remember that the vectors are not exactly the same as points. So to clarify, just a note, we'll get back to that later, is that if we have a PQ is my vector, its coordinates components. Well, let me this way. So P, say PQ, P with the point being, say, XYZ. Okay, Q is a point with UVW. So say a three-dimensional space. Then what are the components of vector PQ? So this one, just as an example, as a warning, an explanation why we care about, we distinguish between points and vectors, is this is an example. What if the initial point of my vector is not, as I want to assume, starts at the origin? So then, what do you think, or what do you think are the components of this vector? X, X minus U. X minus U, right? So X minus U, so that's the change. Vectors are about change. So location is about locations, that where we are, and we're moving from point to the next, and we want to look at the change, and we could look at the change component-wise, or coordinate-wise. So we're looking at what's the change, I'm moving from P to Q, what's the change in the first coordinate? Well, actually, it's the other way, U minus X. It's actually U minus X, and it does matter. So, the final minus the initial. So it's a U minus X, V minus Y, W minus Z. Okay? When P is the origin, X, Y, Z are zeros, and we are in the same place as we were. And that's why the correspondence between components of vector and coordinates of its endpoint is identical. It's the same thing. But in general, this is the more general situation, and as you can see, we have to be careful in that respect. Otherwise, the physics won't work. But this all works in all dimensions. So this will be in dimensional space, and you have n components of a vector for each of the coordinate axes of your space. Okay, so then what remains is the take what we understand geometrically about the algebra of vectors, and just drag it into the high dimensional spaces and see what happens with the vectors. As you can see, the things that will be very predictable. We're going to add and subtract. Let's just illustrate on just sticking with the three-dimensional space. So say if A is equal to x, y, z, and this is a vector. Remember, once again, we're never going to add location. So as you can see, I'm going to add these, and I'm doing it because I can, and I can do algebra with vectors. So A plus B, and then what I do is just simply add them coordinate-wise or component-wise. So x plus u, y plus b, z plus w. I could subtract if I want. Scalar multiplication. Same story. Once again, we do it component-wise or coordinate-wise. And then multiplied by number r, well, let's say a. So a is equal to ax, ay, az. Okay, so that's how you compute if vector is given by its components. That works out in any dimension imaginable, and then we still could do algebraic operations with these vectors, even though the geometry might not be visible as in lower dimensions, but it still works out in the exact same way, and we could verify the algebraic properties as well. That is not a challenge at all. Okay, so questions? All right, so I'll see you next week then.